today's Motwani Distinguished Lecture. As many of you know, Rajiv was professor here at Stanford for many years. I was lucky to be one of his students. Rajiv had a profound influence on not only his students, the area of theoretical computer science, but Stanford in general and beyond, and he's dearly missed. We're very grateful to Asha Jadeda, who's here in the audience, his wife, and the Motwani Jadeda Foundation for providing generous support to theory at Stanford and to this particular lecture series in particular. I'm delighted to introduce today's speaker, Manuel Blum. He's a professor of computer science at Carnegie Mellon, pioneer in the field of theoretical computer science. He won the Turing Award in 1995 for his contributions to foundations of computational complexity theory, applications to cryptography, and program checking. Manuel was born in Venezuela. He came to the US in the mid-1950s to study at MIT. At that point, he had a desire to understand thinking and brains, and he worked in a neurophysiology lab. And then he concentrated on mathematical logic and recursion theory for the insights that it gave him into brains and thinking. He got his PhD in math under Marvin Minsky. He began his career at MIT. After a few years, he joined the faculty at Berkeley, where he was for many years. And since 2001, he's been on faculty at Carnegie Mellon. He's worked on a wide variety of problems throughout his very distinguished career. Some of them include methods for measuring the intrinsic complexity of problems. Blum's speed-up theorem is an important proposition about the complexity of computable functions, and the Blum axioms gave machine-independent ways of understanding the complexity of computation. Since his early work on understanding the limitations of computational devices, his research has focused on innovative ways of finding positive, practical consequences of these computational limitations. And he's figured out ways to turn these things around to obtain secure business transactions, through random number generation, program checking, CAPTCHAs for detecting bot intruders. Every time you complain about entering those things and to authenticate yourself to websites, complain. In addition to the Turing Award, Manuel has won a number of honors and awards. He's a member of the National Academy of Sciences, the National Academy of Engineering, the American Academy of Arts and Sciences. In addition to all his research, an important part of his legacy is with more than 35 students that he has supervised throughout his career, and 3 of them have gone on to win Turing Awards of their own. And his academic descendants have done groundbreaking work in a number of different areas of theoretical computer science. It is my pleasure to give you Manuel Blum.
Thank you very much. So, first, thank you very much for inviting me, and I'm especially honored that it's the Rajiv Motwani lecture. I knew him when he was at Berkeley, and he was a very fine man. So, thank you. So, I wonder what he would think of this title. Can a machine be conscious? Sometimes when I tell this to people, they turn up their eyes. So, I could speak louder. Okay, so can a machine be conscious towards a computational model of consciousness? Let's start by maybe even before this. I've been interested in consciousness for a long time. When I was a junior in college, I apprenticed myself to McCulloch. McCulloch and Pitts were the people that defined the first formal neuron. They proved something that we know now, but they proved that a machine built out of these formal neurons could simulate a Turing machine. So that was very big. They submitted it for publication, and it was rejected. As are most of good papers. They were rejected first round. They were rejected because the neurophysiologists at the time, they said that a neuron had to have both excitation and inhibition, And the neurophysiologist at the time said, we've never seen inhibition. And so it was rejected. Of course, now we know that there is excitation and inhibition, and they were right. I mean, without the inhibition, you can only get monotone circuits. So that was kind of interesting. I could tell some other stories, many stories actually. They were wonderful people. Let's see, so let's start with the definition of what is consciousness. This is an informal definition, of course. Consciousness, and I mean by that conscious awareness, is everything you are aware of while you are awake or dreaming. What you see, what you hear, what you feel, and most especially your own inner private speech. You all speak to yourselves. And you're not crazy, you know, you speak to yourselves. And I've spoken to people that are deaf, and yes, they speak to themselves. They use sign language in order to do this, but they are speaking to themselves. So those are the things we are aware of. Consciousness, by consciousness I mean that conscious awareness. My goal in the short term is to understand consciousness. In the long term, I would like to build a robot that is truly conscious, that really feels pain, not just simulates it. You can find on the web a video of a robot apparently enduring some terrible pain, but it is just a simulation. I would like to, the question I'm asking, it's really kind of a philosophical question. The question is, I just couldn't understand how the body, how the brain is able to get us to feel the agony of pain. How is that possible? What could we do to make a robot, even if you didn't want to make it feel it, how could you make it feel that? I just didn't know. So this is an attempt to understand that. A brief history of consciousness. In 1980, so when I apprenticed myself to McCulloch, and I mentioned that I wanted to understand consciousness, I was told by Walter Pitts, no. He said, you have this much skull, he said, an inch of skull, and the EEG is just getting a very fuzzy picture of what's going on, and we just can't open up people's skulls, and the rats don't speak English. So there was a problem, no consciousness. What's wonderful is that there are many wonderful papers dealing with this problem. So in 1980, the study of consciousness was still taboo. By 1987, a number of outstanding researchers, neuroscientists, philosophers, cognitive psychologists, etc., began suggesting how the brain might generate consciousness. And there's a list here of these people. The one at the Bernard Baars is the first on the list. And Bernard Baars has done the incredible thing. I think his is the main breakthrough that I'll be talking about here. The others are neuroscientists, except David Chalmers is a philosopher, but they're otherwise neuroscientists. In 1990, fMRI was invented, and through its invention, we could now begin to see what part of the brain is working when you do stuff, right? If you have to recognize somebody's face, we know that the fusiform face area is going to light up. There's a particular part of the brain, fusiform face, that for seeing faces. And if that gets knocked out, you will not recognize your husband, your wife, your kid. You will not recognize yourself in the mirror. It'll be really bad. But fMRI tells us where you are seeing these faces. Okay, so can a machine be conscious? I believe it should be possible to build a machine that experiences consciousness, conscious awareness, free will. So I'll talk about this. I kind of like what I have to say about it, naturally. Free will. I think I do understand free will. Pain, I would like to understand the torment of pain. I'll tell you how far I've got. Maybe I've understood it, maybe not. You know, the only way I'll be able to tell is by building a robot that feels it. But even then, is there something like a Turing test to be able to tell if a robot is conscious? That's one of the problems I think about every so often. How can you test if an animal or a machine is conscious? I'll talk a little about that. Joy, the joy of discovery. The machine is to really experience qualia, like the color red, or the ache of pain, and so on, not just simulate the experience. So in order to be sure that we're on the same page, we'll go through a few of these. Number one is one that I'll particularly go through, mentioned a few times. And that's the experience you have of going to a party, and you see somebody you know, and you know you should know their name, but it doesn't come to you. So you go off and speak to somebody else, you have wine with somebody, and then half an hour later the name pops into your head. How did that happen? How did the name pop into your head? Well, in fact, your unconscious was working on this problem. You consciously said, I want that person's name, and the unconscious part of your brain, one part of it says, the name begins with J. Another part says, oh, I met him at a conference. And finally, this information gets together and you get the name popping into your head. So I think you've had that experience. I'll just refer to it. Breathing can be conscious, but of course it can be unconscious, and mostly we breathe unconsciously. Except now that I've told you that breathing can be conscious, you're all aware of the breathing. It's just terrible. Selective attention, learning to ride a bicycle. You know that you really pay attention when you are learning to ride a bicycle, but now you don't have to do it. You can hop on the bike and go. And most of you really don't know how you ride a bike. Do you know how you make a left turn on the bicycle? Do you know?
You lean.
You lean. Now, Carl, I'm sorry to tell you that if you lean to the left, the bicycle will lean to the right.
That's true.
So it doesn't happen that way. How do you turn to the left? How do you turn to the left?
Turn slightly the other way.
Turn the handlebar the other way. So the other way is right.
Yeah.
You want to go left? Turn your handlebar to the right.
Yeah.
What does that do? You're moving along, you turn the handlebar to the right, the bicycle wants to go to the right, momentum is carrying you straight ahead. So you're going to fall to the left. And then you turn to the left. And you don't know this, and yet you're doing this every time you want to make that turn. So, the sighted world versus the blind-sighted world. So there are people who get a trauma, a hit to the head, and they become blind. They simply, let's see, maybe I do need this. They become blind, so they can't see. But it's something called blind sight. You can put them in a room like this and say there's a door at the other end, and go to it. Well, I'm blind. There are obstacles in the room. There's no way I can do it. Just try. Keep your eyes open and just try, and in fact they manage to do it. It's called blind sight. They really are able to see, but they're not conscious of that fact. Problem clarification, incubation, the Necker cube. Oh, ping pong. Let me just mention about ping pong. This is well known. If you play ping pong, people are taught ping pong have to think about what they're doing, but when they get into a tournament, they're told, turn off the conscious thinking. Let your unconscious brain do it. And then that works much better. Okay, so here's the Necker cube. It's just a cube, just an ordinary cube. I need it for understanding consciousness. There are two ways you can see this as a cube. You know, if it's filled in, the way you could see it is you can see it with the lower left square being in front of you. You're seeing it essentially from above, the lower left, or you can be seeing it from below, and then the upper right-hand square is what's in front. So either this square is in front, this blue square, or that blue square. One or the other is in front. And you see one or the other when you see the cube. And you can see both at the same time, but it's not easy. You can sit at this and try really hard, but your brain does not want you to see both. It is trying to get you to see one. And this will turn out to be very important in what we say. Basically, there's one world out there, and it's really important that your brain get it right, that you see what is really there. And there are many parts of your brain that are suggesting it's this or it's that, and you want to get it right. Necker cube. Oh yeah. Oops. Look at this photo. This is actually, this upside down house is in Moscow. You can see they finished building it a few months ago. It's supposed to be a really great tourist attraction. And if you go in, you see that all of the furniture is glued to the surface. Okay? Here's a better picture of it. Let me just point out that you feel like you're seeing the whole thing. But actually, your feeling is that you are conscious of everything. What you feel you're conscious of are things that you can know if you pay attention to them, but you really don't know. Do you see the bicycle? There's a bicycle there. Do you see the trash can? There's all sorts of stuff that, there's a doghouse. Do you see the stairs on the right, which is you take to get up into the house through its front door, but of course upside down. The point of that is that when you see something, like here's a photo of a cable car, this picture is supposed to show you what a person sees when they're focused on the letter E on the cable car. That part is a nice clear focus, but the rest is not. Nevertheless, you get the sense that the whole thing is in focus. Okay, so my view of consciousness. So my view, it doesn't have to be your view, but my view is that consciousness is a property of all properly organized computing systems, whether they're made of flesh and blood or metal and silicon. And my thesis is that it's the architecture of these systems that makes them conscious. It doesn't matter if they're made out of neurons or if they're made out of transistors. It's the architecture. And that my job as computer scientist is to use the experimental evidence provided by neuroscientists. They call it the neural correlates of consciousness, and the models that neuroscientists propose, and they're quite good models, to create a formal mathematical model of a conscious computer. I would like something where I could well enough defined that I could start to prove theorems. The model should provide, among other things, reasonable explanations of consciousness, free will, and the various emotions of love, joy, pain, and so on. And I'll be going through these, and if you're not satisfied, then please tell me that. I would like to know that, because I really want to make sure that you can see, that we can see our way to this. So my conscious computer, let me just mention this, is at best a gross simplification of a real brain. It is even less related to a real brain than a Turing machine is related to a computer. So here's the point. I am not trying to get an exact model of the brain. I may have worked in the neurophysiology lab. I worked with, on cats. But I'm not trying to get a model of the brain. I'm trying to understand consciousness. And I would like, for example, I would like to be able to say which animals and or machines are conscious. Are dogs conscious? What do you say? Are dogs conscious? Yes. Octopuses?
Yeah.
Insects? I see people. Robots? Could they even be conscious? Why these and not those? I'd like to be able to answer these questions. Okay? The fundamental extraordinary idea for explaining consciousness. I really tried for a long, long time to come up with some explanation how the brain can make you feel the agony of pain. Lenore would like me to talk about the ecstasy of joy, but it's been pain that's been on my mind, so I'll talk about that. I could not come up with something, and until Baars came along and gave a model, which I love, which to me carries a lot of explanation. It's Baars' theater of consciousness. And Bernie Baars describes conscious awareness through a theater analogy. Let me just mention the fact, so I'll go through this and you'll see his analogy, his model, then my model, which is just an attempt to make it a little more precise and mathematical so we can prove theorems. And let me just mention that I believe we can make robots really conscious, and Baars is very doubtful of that, even though it's his model. So the question is still open. His theater analogy is this. Consciousness is the activity of actors in a play. They're performing on a stage, which nowadays would be called working memory, but I'll call it STM, short-term memory. There are many short-term memories, short-term memory, and their performance is under observation by a huge audience of processors. You people, you are the unconscious part. A huge audience of processors that are sitting in the dark. Well, not that dark, but nevertheless, sitting in the dark. And the meaning of this is that you are conscious of what's on the stage, but you are not conscious of what's going on in that audience. You are conscious of the fact that you want to know his name, the person that you saw in the party. You are not conscious of how the thinking that's going on that eventually leads you to it. Okay? So in the Baars theater, each LTM, long-term memory processor, is knowledgeable of and concerned primarily with its own unique specialty. Each is in close contact with others that have or might have relevant information, and these long-term memory processors are unconscious. You're conscious of just a little bit, and it's kind of nice that you can pay attention to what it is you are conscious of and see. I would hold a nice cold can of Coke in my hand to try to get to where is the agony coming from, and I can assure you, you cannot do it. You will not be able to get back to what's going on in the unconscious to generate that agony. Here's Baars' theater of consciousness. He calls it the global workspace model for reasons you'll see. And he even draws a picture, I'm so glad he did, because this is somewhat like a Turing machine. With at the very top there's in yellow you see this CPU, the finite state machine. On the left you see inputs coming in, on the right there are outputs. There's short-term memory in the middle here, and at the bottom are all these processors involved with long-term memory. Okay, so what accounts for consciousness? I've said this, I'll say it again, the architecture. There's a tiny short-term memory, Baars stage, capable of holding at most a few chunks. You've heard of chunks. George Miller came up with this paper, the magic number 7 plus or minus 2. You can, if somebody tells you a phone number, 7 digits, you can remember it long enough to go and find paper and pencil and write it down. But nowadays, when they're 10 digits long, you can be in trouble unless you know already that the first three digits. Right? It's hard to hold 10 chunks. These are chunks. And chunks have never been defined. He says a chunk is a digit or a letter or a word. He gives examples. A sentence could be a chunk. That's as far as it goes. I'm going to tell you what I think a chunk is. I think a chunk, and it comes out of this model, I think a chunk is a pointer into long-term memory. So there you are, you're in short-term memory, and you want to know something, and some unconscious processor says I have it, and it's a pointer into that unconscious processor. You maybe are interested in the alphabet, A, B, C, D, E, F, G. There's a pointer to the beginning. It's in somewheres there, and that pointer could be the chunk. So, question? No? Okay. Did I finish there? An enormous long-term memory, the audience of unconscious processors. Contents, here's the point. Contents of short-term memory are steadily broadcast to all long-term memory, the audience of unconscious processors. You all are hearing me. I'm broadcasting to all of you. Long-term memory processors, now some of you may have the information that I'm looking for, and it will come back to me through negotiations. You may have different, the Necker cube, one of you has one view of the cube, another one has a different view of the cube. These have to, you need agreement, and one of them gets up into consciousness, just one. So here, I'm now going to show you this conscious computer. There's a CPU at the top, the central processing unit. This is the stage director, is what Baars calls it. And for a while I was going into what the CPU looks like. Turing has a finite state machine there, and he has some number of states, and you know how it works. You're in some state, and then input comes in, and then you output something, and then you go to a different state. If you try to do the mathematics here, you find, well, what could be, how many states are there? Well, there are 7 plus or minus 2 chunks, and each chunk, if you count the number of chunks, there, 10 bits to a chunk, and you do the calculation, you find out there's many states here as there are atoms in the universe, in the visible universe. We don't know about the whole universe, but the visible universe, 10 to the 80th. So I did, there's one of the slides where I do the calculations. I won't do that here. It can't be that way. And, but nevertheless, it could be a CPU. So I've replaced finite state machine by CPU because that can actually have the number of states we want. Here, there's short-term memory. That's what we're conscious of. We're conscious to some extent of the input coming from, you see the input on the left. We're conscious to some extent of output. And I've got colors here. The yellowish color denotes conscious. The light yellow denotes partly conscious. And the gray will denote unconscious. Okay, so now let me go through the model. And this is what, this is an informal description of what I would like to make completely formal. So there's conscious, unconscious. The unconscious processors, the faces, that's the fusiform face area. There's speech. There's the Broca speech area. There's the Wernicke speech area. There's fine control in the cerebellum. There are processors for lots of different things. And these processors are the processors that are looking at what's in short-term memory and trying to figure out what's going on. The stuff up in short-term memory is being broadcast to them, and that's this picture. What's in short-term memory is broadcast to all of the processors. They are all on the same wavelength as you. I have just one tree here. There should be something more like 7 plus or minus 2 trees, because there are 7 chunks up in short-term memory, but basically every processor gets to see them, gets to see it. This direction is fast. It's fast broadcast. The reverse direction is much slower. And it has to be slower. The reverse direction has to be slower because you can have 2 processors with information, and maybe the information has to be brought together into one, or maybe just one of them gets to go up. Sorry. I've got too many things in my hand here. You can talk to yourselves. Talk to your neighbor. Introduce yourself to your neighbor. Say hi. You want it like on this. Thank you. Yeah. Okay, so where were we? I've got too many wires here. Okay, so we were fast broadcast down, but very much slower resolution and integration. So fast broadcast down, what's the name of that person? And then the information has to be collated and collected and raised up. And half an hour later, it's Joe. That's where you find out. Okay, that's a main important part of this whole thing. So how does this account for consciousness? So consciousness is the awareness of by all processors, every single one of them, of all the activity on the stage. Sometimes people wonder, why just 7 plus or minus 2? Why is this short-term memory so very tiny? But the fact is that every single processor has to know about everything on the stage, and those processors aren't too big, and they can't see much more than the 7 digits that you can remember. They can do that, not much more. So it has to be small. Consciousness is the awareness by all processors of all activity on the stage. Consciousness arises because the activity on the stage is broadcast to all of the long-term memory processors. That's the... Any questions about that? You may or may not agree. You look like you...
I have a question about external input, like when you say that there is the upward direction.
You have a question about, yeah, external input, upward direction, right?
So the integration to upward direction, so we say it's read only, so. Or it's not.
It's the information is just going up. It's just that's the information that gets up. You want to know somebody's name. If you don't know where that information is stored, you have no idea at all. But if some processor knows that you want it and it's willing to give it to you, then that information will eventually get up there. And that's what this is doing. Of course, two different processors might have 2 different names. You really want to get the right name. Okay.
Right. So since the brain is so enormous, some of these processors might have sub-processors that aren't on the...
Yeah.
Processors already, and you're just helping yourself to them, and it's not clear what work the architecture is doing in explaining consciousness.
Let's see if I can... How to do this. I would like to... See, it keeps on going to the right. But how do I get to see what's on the right here?
Oh, you want to move this thing?
Yeah, I want to...
That's not what you want to move?
No, I've gotten off the...
Oh, I see.
I haven't shown you... maybe I didn't choose the right ones, or all of them, but there's a whole long list. I won't do it. Something's not working here. We'll leave it at this.
Okay.
Yeah.
Let's go back. Okay.
Okay. So, yeah, if you keep on going, you would see that there's a huge number of processors. This is just a taste.
No, that's not the problem. The problem is you say you're going to give us a theory of consciousness. You're going to explain, why it is that fear feels the way that it does, and why desire and love feel the way that they do. But here, you're just saying these processors already have memory and desire and love in them. You haven't explained what it is about the processor or about where it sits in this architecture that gives those things.
No, and I'm not going to tell you how these particular processors work. I mean, they have names. I already mentioned the fusiform face area that sees faces, and I'm not going to tell you anything about how it works or anything about how any of the other processors work. So what am I going to tell you?
How these experiences work together, and that's
No, I haven't explained it yet. But so in what I imagine for this formal model is I'm going to simply define what's in that short-term memory to be what's conscious, period. Now, this may seem a funny thing to do, but that's what we computer science theoreticians do. You know, there's this notion of zero knowledge, which has been defined. It defines exactly what is or is not a zero knowledge algorithm. If you look at it carefully, you'll see that there are all sorts of things that are being given away by zero knowledge proofs. It doesn't matter. It's just called zero knowledge. We have a definition, and we start to prove theorems. I'm going to simply define whatever is in short-term memory, and it's not very much, as what's conscious. Now, if you accept that, then for the moment, then I have to give an explanation of what follows and why one should believe this. That has still to come. Okay, so how does this account for emotions? The unconscious long-term memory processors, which generally respond to questions, requests, and commands from the stage, can, when necessary, force themselves onto the stage. There are certain things you can ask from them. I have wanted to be able to say, I'd like to see this audience in black and white. And there's no processor in my brain that will let me see that. I see color, or maybe if it's very dark, I'll see black and white. But basically, there's plenty that the processors can't do for me, and there's some things that they don't want to do for me. There are some things that they are willing to do, try to do for me. But one interesting thing is that processors on occasion can force themselves onto the stage, and long-term memory processors responsible for motivations like hunger can insist to get through, as can processors that alert to pain. We know something about where in the brain pain arises. We certainly know a lot about where fear arises. That it arises in the amygdala. But these processors can actually force themselves onto the stage. The conscious emotions arise in part through those processors forcing themselves onto the stage. There's a wonderful story. Have you read Oliver Sacks? He has many wonderful stories, and he talks about one that he was hiking in the Swiss Alps, and he saw this field, and he saw a sign, "Beware the bull." Well, didn't see any bull, so he walked into the field and kept walking for a while, and then at some point, suddenly, he saw the bull. And when he saw it, he could see the bull getting up on its haunches, and it scared the living dickens out of him, and he turned around and ran as fast as he could out of that field. And it was only when he had finally left the field that he realized that he had torn some ligaments. If you've ever torn a ligament, it is the most terrible pain short of childbirth that you can imagine. It's really, really terrible pain. And people who tear a ligament will throw up, and when they get that, it's an awful pain. Yet he didn't feel it until he was out of that field. I could just see the fear and the pain working their way up, and the fear or the pain, one of them is going to get through to consciousness, and the fear says, no, I'm going to get through first. I'm the important thing. And that gets up, and only when it finally releases the stage does the pain get up there. Yes?
The addiction, so addicting emotions, right, or addictions of various kind, are they an instance of LTMs forcing themselves onto the stage?
So the question is, where is the emotion coming from? Is it from the LTM?
Especially if it's an addiction, right? So, for example, let's say obsessive behaviors like pulling one's hair or biting teeth or something.
Yeah, that's a very interesting question. I have to think about that, and I can't answer that. I'm at the point where I can say that a processor can get up on the stage. And but I haven't thought. I bite my nails. Terrible. You don't want to do that. And so I would really like to know, but don't know. So let's look. So here's what I've done. I I spent a bit of time trying to understand which of these LTM processors are necessary for consciousness and which are not. And the ones that are marked in green, I'm claiming, are necessary. They're necessary because the model, which I'll be showing you, or to some extent has started to show you, that model requires these green ones. And then there's the fact that people who don't have these green ones, as far as I know, I've not been able to find an example of a person who's missing one of the green ones that's conscious. The red ones don't seem to be required, and these red ones are ones that I can, for each red one, I can give you an example of a particular person who doesn't have that ability and is conscious. So if you look at number 5, for example, declarative memory creation, there's this wonderful, have you heard of this person, H.M.? He's the psychologist here will know. His name actually we now know is Henry Molaison. He underwent some surgery because of, well, epilepsy. They needed to do some surgery. They cut some wires from the hippocampus up to the cortex, and after that, he could not create new memories. None. So, well, none of what are called declarative memories, the kind of memories that you have that tell you about what you did today or yesterday, words in the dictionary, stuff like that. This person was studied for 20 years by a particular woman who would each day come into the room and introduce herself to HM, and HM would meet her, and they'd go through that day's trials, and after she left, he lost it all. He could not create these new memories. It's really interesting. On the other hand, he did, so let me say something about this through HM. HM had inner speech. I'm saying that you need that for inner speech. You need to be able to plan what you're going to do. He had self-awareness. He was aware, he could separate himself from the rest of the world. And there are cases of people who get knocked on the head or who have some kind of damage, and then they can't separate themselves from the world. And I'm saying if they can't do that, they're not conscious, or they will not have the same level of consciousness. Motivation, you need to have desire and energy to do stuff. And HM had these things. Procedural memory, I've been looking for somebody. Procedural memory is the memory that enables you to remember how to ride the bicycle. You learn to ride the bicycle, it goes into procedural memory. 20 years later, you can still ride the bicycle. It's wonderful. It's still stored there. I haven't been able to find one who I'm looking for to try to make it red, for example, somebody who doesn't have procedural memory but is conscious. Can't find it, so this is still an open question here. Procedural memory creation. Where am I? Yeah, so I'm started to, that HM did not have declarative memory creation. He did have language for outer speech. He did have face recognition. He did have emotions. But nevertheless, there are people who, there's a person who doesn't have any emotions. Caleb, I don't know if I'm going to, let's see. Well, let me go, I'm losing track of what I'm doing here. Let me go through this green stuff. I'm saying the green stuff is necessary for consciousness. And 1, 2, and 3 are inner speech, self-awareness, motivation. And that comes out of the model, and I won't say how it comes out of the model, but let me tell you that there is a test of consciousness that the psychologists have. You know about this? It's called the mirror test. It's a wonderful test. You dab a bit of paint on the elephant's forehead, and then an hour later you introduce the elephant to a mirror, and it looks and it sees itself in the mirror. First of all, the elephant knows that it's it in the mirror. and it sees the paint, and then it, after a while, it picks up its trunk and tries to take it off. You're seeing here inner speech. You need to have inner speech to be able to actually decide that you're going to take that trunk and try to get that white stuff off. Self-awareness certainly is coming up in this, and motivation, the energy, the desire and the energy to actually get it off. So that's the mirror test, and I never really understood the psychologists thinking that this was a good test of consciousness until I saw, wow, this is testing for at least these three things. Okay, so those three things. Let me talk about the three things. Inner speech. So Jill Bolte, Scott Moss is a psychologist who was victim of a stroke, lost the ability to use language, and was able to recuperate and relate his experience. And these are his words: I had lost the ability to converse with others, to engage in self-talk. In other words, I did not have the ability to think about the future, to worry, to anticipate or perceive it. Sounds great. At least not with words. Thus, for the first 4 or 5 weeks after hospitalization, I simply existed. And there's some place where he says that he existed but was not conscious, a certain notion of consciousness. Jill Bolte Taylor, she's got a wonderful book, My Stroke of Insight, really fun reading. She experiences massive stroke, and you get some insight from her. Losing inner speech, she experienced a massive stroke, resulted in a complete loss of inner speech. As she later described in her book, losing inner speech also led to problems with self-awareness, loss of biographical memories, and even those emotions related to self-consciousness. There's a loss of a kind of consciousness there. Here's self-awareness. It's needed in order to include oneself in one's plans. So on the stage, you need to have a person that represents you. That's you. And that you may want to, as a baby, you can imagine a baby discovers it can move its arm. Isn't it wonderful? You can see it in the crib. It's discovered that it can move its arm, and then it looks at its foot. And gradually discovers, wow, it can move that foot too. And then it looks at the mobile, and it doesn't seem to be able to move the mobile. It's learning what is baby and what is not. So self-awareness is really important. And I'm getting some confirmation from Alzheimer's, because people in the last stages of Alzheimer's are self-aware. They are conscious. They are self-aware. They may not be able to remember their kid, but they are aware of themselves. Then I'm talking here about the mirror test. Animals who pass the psychologist's mirror test, they include orangutans, chimpanzees, gorillas, bottlenose dolphins, it's wonderful, elephants, I just mentioned, orcas, bonobos, which is a kind of chimpanzee, rhesus macaques, magpies, a bird. The same thing is true with the birds. You somehow surreptitiously paint some white on their feather, and when they see themselves in the mirror, they try to get it off. Dogs and bats don't pass the mirror test, but it's sort of unfortunate. Dogs don't see that well. We need a different kind of test. Bats don't see at all. They hear. So it's not surprising that they don't pass. And this is not a perfect test. I can imagine building a robot that would pass the mirror test, and I wouldn't say that it's conscious. I would like to have a good test of consciousness. What does it mean to not be self-aware, at least in part? So there are diseases of self-awareness. Anosognosia, A is without, gnosia is knowledge, anosognosia, without knowledge of yourself. It's a disease. Asomatognosia, without knowledge of yourself as a body part. There are people who, because of damage, who because of damage don't believe that their leg is their own. They just don't believe it. And it goes to such an extent that they ask their physician to cut it off. It's not theirs. In this country, the physicians won't do that. The surgeons will refuse, so they go down to Mexico, and the Mexican doctor will in fact cut off the leg, and they're happy after that. They can't walk anymore, they have to be in a wheelchair, but they're happy because it wasn't part of them. That's asomatognosia. Terrible. Motivation. So here's an example of motivation. You know, I'm saying you can't be conscious without motivation. Fortunately, there are some people that lose some part of their motivation, and so you can still test them. An important one is this left hemispatial neglect. I've actually not found any right hemispatial neglects, but there are many left hemispatial neglects, and it correlates to a loss of consciousness. You show such a person the picture on the left of the clock, the house, and the flower, and then you ask them to copy it on a sheet of paper. And you see on the right what they've copied. They see the clock, but they only see the right half of it. They see the house, but they only see the right half of it. They see the flower. They're only conscious of the right half. They're not conscious of the left. You put a plate of food in front of them, they will eat the food that's on the right of the plate, and they'll be hungry, and you'll say, well, why don't you just turn the plate around? It will not occur to them to turn the plate around because they are not conscious of that left half of the plate. So I'm basically saying that they have lost consciousness, they have lost that motivation. Here are some specific instances. HM had inner speech, self-awareness, and motivation. He could also create new procedural memories, so this was interesting. You come in, and this woman came in with a sheet of paper and said, I want you to type what's on this paper on this blank sheet. And HM said, I can't type. Well, you know, sit down and try. And then he sat down and he discovered that he could touch type. Oh wow, I can type, was the result. Of course, when the next day he didn't know that he could touch type. He did have that procedural memory. He had created it, he had learned to type after this operation. He could create new memories, but they were these types of memories like the riding a bike memory. Emotions, fear, embarrassment, guilt, anger. I can show you somebody in each of these cases who is missing these. Caleb, especially like, feels no emotions, has never felt any emotions. And fMRI confirms this. The part of your brain that lights up when you're in love does not light up in his brain. Same for the other emotions. Nevertheless, he's married. He got married. His wife understands that he doesn't feel love. It's too bad. Yes, question?
So you mentioned motivation as being essential to consciousness, but what about, say, severely depressed people who lack pretty much all motivation and just lie in bed all day?
Yeah. They're beginning to, yeah, they're very severely depressed patients, and there are people with catatonia who actually, they can have something burning them. They can be standing against a radiator that's burning hot, and they don't move away. And, right. Sort of hard to tell, isn't it, when you can't even get them to say anything. The depressed person often can talk, but these catatonics, it's very hard to get them to talk. You basically have to get them back to some kind of a normal place where they can talk, and then ask them, were you conscious? Do you remember? The examples I've seen, they don't. So here, psychologists use the mirror test as a test of animal consciousness. I've already mentioned this. Still missing, there's nothing in this model about intelligence requirements. This is something that I am missing. There is intelligence is required to decide what gets through from long-term memory to short-term memory. How are these decisions made? Which of fear and pain will get up to the top? These decisions have to be made, and I'm not sure just how they're made. This is all down in the long-term memory gray area where I don't quite know the details of how it's done. But I can say this, long-term intelligence is not required short-term intelligence. So long-term intelligence measured in days is not required because HM doesn't have it. Short-term intelligence measured long-term intelligence measured in days, HM doesn't have. Short-term intelligence measured in hours, you have to have. The requirement is that you be on the stage, 3 requirements. Self-awareness, you have to be on the stage. There's inner speech, you can talk about what yourself and others are doing, and motivation to actually do stuff. Question?
Doesn't the CPU in your model do this? Isn't that the intelligence? What does it do if it doesn't do this?
The CPU is there to, it's like the finite state machine. It's there to tell you when you're in this state with this content in memory, and this is the input, you should produce this output and go to that state. Now this is actually done because you're in this state and some processor wins its way up to the top and it now is taking over the stage. So
It's a mechanical thing, it doesn't prioritize which one should.
Here the CPU is intended to be a purely mechanical thing. I think it actually, I painted it in gray. We are not conscious of it. We don't know how the thing works. We are as unconscious of it as anything else. It's a little separated from everything else because when you, as I will speak, when you get into some terrible pain, for example, basically the processor for pain gets up on the stage and doesn't allow anything else up on the stage. That's it. Nothing else. And every processor sees that you're up on the stage. It can't get through. Every processor sees that you're claiming to be in pain. It's when all the processors in your head are seeing that there is this pain that in fact you will feel pain. Nevertheless, that central processing unit is what enabled Oliver Sacks, even with fear and pain, to get out of that field. There's something there that's still able to get you moving. It's a little different from the rest. I'd like to be able to answer better, but that's what I have. Here's a point. I think I've run out of time. Try to go fast. Supercomputers are not conscious of their world, but they are big enough. The Titan supercomputer has 1.7 times 10 to the 15 transistors. I think of a transistor as being roughly like a synapse to a neuron. The human brain has just about that number of synapses. I equate transistors to synapses more or less. I don't believe the Titan supercomputer is conscious, doesn't have the right architecture. The architecture I'm demanding is this thing of the short-term memory, which everything in short-term memory being broadcast to all the long-term memories. That's what I require to have consciousness. So my goal in defining the conscious computer is to understand things, conscious awareness, free will, motivation, emotions. Kind of running out of time. Let me just, okay, quickly, hopefully, quickly. Not more than, okay. The paradox of free will. Free will was a problem for a long time. This is from a century before Christ. Lucretius wrote a poem, De Rerum Natura. It's the only thing of his writing that survived. And this is his writing. If all movement, it was in Greek, but this is his writing. De Rerum Natura, that sounds like Latin, but, well, maybe it was in Latin. If all movement is always interconnected, the new arising from the old in a determinate order, if the atoms never swerve so as to originate some new movement that will snap the bonds of fate, the everlasting sequence of cause and effect, what is the source of the free will possessed by living things throughout the earth? It's a question, right? And it's an old question. Yes?
Well, was asking a question until recently. So, there's an addition here, because the movement is a second degree equation, and so you need to know both location and momentum, and the no for quite a while, so impossible to do at the same time from...
I don't think quantum effects have anything to do with it. I think that even in a completely deterministic world, not quantum world, you will still have free will. So let me tell you why. You will still have free will. This was just a point that is an old question. Here's another person questioning the same thing. Samuel Johnson, with his very pithy statement, all theory is against the freedom of the will. All experience is for it. He lived just about the time that Newton was at the end. He knew about Newton. He thought of, we have a deterministic world, and in that deterministic world, all theory, Newton's laws, is against the freedom of the will. You don't have that. All experience is for it. You certainly feel like you have that ability. And and I'm going to claim now that my explanation of free will does not require randomness, does not require anything quantum. And let me also go into this. The solution beautifully explained by Dehaney, one of those people I mentioned. Our brain states are clearly not uncaused and do not escape the laws of physics. Nothing does. But our decisions are genuinely free whenever they are based on a conscious deliberation that proceeds autonomously without any impediment, carefully weighing the pros and cons before committing to a course of action. When this occurs, we are correct in speaking of a voluntary decision, even if it is, of course, ultimately caused by our genes. So I explain free will like this. You're playing a game of chess. You often in chess, I know I should either move this bishop here or this knight there. There's one or two possible. And I simply cannot tell which one until I have actually computed the result of making those movements, each of those movements, and then I can say this one seems to be the better movement. You have free will until you finally decide what it is you're going to do, and when you make that move, of course, you don't have that free will anymore. So there's free will. I'm going to end just by saying, well, I don't really want to end, but that about free will that that I think the reason these ancients didn't understand, weren't comfortable with the notion of free will is because they did not know complexity theory. Complexity theory tells you that there are some things that you simply cannot compute in less than a certain amount of time. And deciding which of two moves to make, well, you simply can't compute it in less than a certain amount of time. And with complexity theory, you basically do have free will until you finally come to a decision. Okay. I was going to talk to you about the homunculus. This is a homunculus in a Mark Bullwinkle sculpture. You see the little head in there? That's the actor on the stage. That's all that the homunculus is. How to simulate emotions. Okay, I'm going to keep on anyway. Look, if you feel like going, go. It's perfectly okay. I'm okay with it, but I really want to tell you at least about pain. So, about pain, I think I've already mentioned to you, I want to distinguish between insensitivity to pain from indifference to pain. There are people who are sensitive to it, but are indifferent. And we know lesions of the insula may abolish that agony. Typically, patients report that they have pain but are not bothered by it. They recognize the sensation of pain but are immune to suffering it. So now I want to tell you how to engineer pain. And of course, I don't know how to prove this without actually building a robot. How to engineer pain. First of all attention is on the pain. Take away free choice. I'm talking about real, serious pain. When you tear a ligament, that pain, that gets up on the stage, and all of your brain knows about that pain. I mean, if there's anything that could be conscious of it, it is aware of it because it's up on the stage and it's broadcasting pain. There are other things, like reactions to pain could be made automatic, cat on a hot tin roof, generate sweat and increase heart rate. The question is this enough will a machine feel real pain when it loses control and free will and is forced to pay attention to the pain? How to engineer pain. So this, I worked in this neurophysiology lab. Wall had the laboratory next to me. Wall got very interested in pain because he was constantly working on cats, cut off the tops of their heads, put in probes to see what's going on. He was definitely aware of the fact that can be very painful. And so he actually spent his life on pain. He wrote, this is fairly old, 1965, "The concept of a pain center in the brain is pure fiction unless virtually the whole brain is considered to be the pain center, because the thalamus, the limbic system, the hypothalamus, the brainstem reticular formation, the parietal cortex, and the frontal cortex are all implicated in pain perception." And this is basically the point I'm trying to make, that it's this broadcast to all of the processors in the brain that would generate the pain. Well, then I talk about fear, motivation, embarrassment, joy, cravings. Bibliography on consciousness is the same one I showed before, and that's it.
At Google X, I think they recently ran into something called the avatar robot at Google X. And what they had is, so let's say it's Moses, let's say Moses is the avatar robot. They only have developed it. They actually brought it in from Israeli defense people. So if they put an AR, VR, sort of glasses on my eyes and on my ears, and they take away just two senses, which is seeing and hearing, and put it onto the avatar robot, then in a few minutes, I start believing that I'm that robot, and actually that they can cut my skin here, and I may not feel it. So it's a very interesting thing about pain and consciousness, and I think you might want to see it someday. Happy to give you towards.
Thank you. Yes.
I know we've had a lively discussion. Are there more questions?
Hello.
Hi.
I was curious how you plan on breaking down all of the LCM into the individual processors, like how you will decide exactly what is contained within one or the other.
Well, actually, in the brain, we know that a lot of these processes there are many processors that are concerned with the same sort of thing, like with speech. Broca, Wernicke, two different processors. There's a lot of this going on in the brain. But as I said, I'm not trying to figure out how the brain actually works. I just want to build a robot that's conscious, and that robot doesn't have to have that problem. We can put the processors that we want to do things where we want them. I don't know that answers your question.
Okay, so I have one of these microphones, so can I ask you a question? So, in your explanation there at the end on pain, you talked about getting the robot or the brain to be all focused on the pain.
The pain, right.
And that would be an indication, I guess, that would be real pain.
Yes, which is what I'm trying to
Okay,
understand.
so, I don't know if you've ever experienced this, but like I have a couple of kids, and a favorite example that I like to use is walking through the night, I hear a noise, and I go out and I step on a Lego brick.
Yes,
Right?
it's
So
painful.
There's a certain exquisite kind of pain you feel when you step on a Lego brick. And that is very different. And yes, I will agree, a lot of my, sort of inner focus, I guess, if I put it that way, is focused on that pain and how to jump up in the air or whatever to get rid of that. But that is completely different from the pain that I feel when I prick my finger with a pin, or when I by accident touch a burner or whatever. So
Yeah, there are different kinds of pain.
yeah, so those are qualities, those are qualia, they were feeling specific properties that we're immediately aware of.
Yes.
So I can understand the computational model. I mean, like with Baars, it's the computer scientist's dream. It's all sorts of processors that you can use their own and connect with.
But you understand that when the pane is up there, the pane is saying, I'm requiring that you have yourself up there. There's an actor there representing you. And when you step on that Lego, you know that it's that toe that's pane, and there's that pointer. So all the processors know.
I can understand, given pane, given some element that you can then compute as the pane, as like the object, you can then have all sorts of responses and stuff like that, which are appropriate for feeling pain. But what about that painful qualia or quale itself, that particular painfulness of stepping on the brick or poking yourself with the needle or whatever? How do you get that into your robot? Because that's the hard problem of consciousness.
No, it'll simply show up in a different way. One kind of pain happens to be this toe. Another kind of pain is a pin in the hand. The actor is there. You know where the pain is occurring.
Okay, you know where it is, right? That's a
And you know how intense it is.
You know how intense it is. But what about the pain itself? How do you explain that? That's
I'm saying that it's that no other processors can get up on the stage. That in the case of pain asymbolic, the other processors can still get up on the stage. In the case where you're feeling that agony, what's causing the agony is that no other processors can get up there. Nada.
So no other processors getting up there, is that what composes the painfulness of that?
Yeah.
Okay,
That's what I'm saying composes the pain. Now, you might feel that that's not enough. Sorry, that's what I'm saying.
Over here. I just wanted to ask, what kind of tests do you plan doing to see if you've successfully built the conscious robot?
What kind of test?
Yeah.
As I said, I'm really trying to figure out what would be a good test, like the mirror test. So I would start with the mirror test. The psychologists use the mirror test for awareness. But, I think there are levels of consciousness. I can imagine looking in a mirror where you don't see yourself. What you see is some hologram of yourself. And you move a finger and you see all kinds of movement. But somebody else moves a finger, you don't see anything happening up there. I can imagine, all I'm saying is I'm imagining that the mirror test can be pushed to the point where you really require some intelligence to be able to understand what's going on. That would be an example of how I would push the mirror test. But the answer to how to really test for consciousness, that's a great question. I've asked many people. No one I know has a good test for it. I will keep on thinking about it. I intend to find something, because nobody's going to believe me until I find something like that.
Yeah. In addition to the computational, excuse me, in addition to the computational complexity thing that you mentioned in terms of free will, the sheer number of steps that it takes to go from here to actually get to your conclusion, your decision. There's another aspect of it, it seems to me. Since these are asynchronous systems, there's the arbitration time involved.
Yeah, that's why going up is taking so much more longer than coming down.
It's not surely the number of steps, the computational complexity, it's also the arbitration.
Yes,
complexity.
absolutely.
And that arbitration also gives you space for free will because it inherently imposes delays.
It certainly imposes delays, yeah. Good. I agree.
Yeah, so I had a question about when we were saying
I'd like to get these questions. Please, you should feel free to go. This lecture is over. But I would like to get the questions because I'm learning from them. So please, go ahead.
Yeah, so when we were deciding the checklist of these things are necessary for consciousness and these other things aren't, it seems like all the bullet points were somehow able to be empirically evaluated, like you can measure the MRI.
Right.
But my question is, so it's just to clarify, it's not the case that we can evaluate these guys are conscious and these guys aren't, right? It's heuristically, we think that if you lack motivation, someone who's catatonic, perhaps is not conscious, right? And I guess the point I want to raise is
So isn't this somehow circular? Like if you ask someone like, did you feel like you were conscious at the time? You're like, what do you mean? And then you say, like, were you able to like recall what was going on? Or like,
Okay, let me try to answer. I think I understand. I'll answer with something that was only discovered in March. In March, we discovered that a small part of the brain called the claustrum seems to be the broadcasting from the stage. The claustrum actually broadcasting and receiving. The claustrum has about 100 neurons that actually are known in the rat, for example, to go completely around the brain. They just go to every single part of the brain. These are amazing neurons because they have these longest axons going to the most places in the claustrum, this very small claustrum. We also, so Koch, who talks about this especially, says that seems to be where the broadcasting is being done. We now have example of one and only one person who, because of epilepsy, went under the knife. And you know, when they open up a person, they go in, they will probe by putting in electricity into wherever they're going. They want to make sure they're getting to the right place. They went near the claustrum, and when they put in the electricity there near the claustrum, the person stopped. Completely stopped. It was just nothing. Stopped. And as long as it was there, it stopped. And then you release the electricity, and the person's awake again. And you ask, what happened? What happened? They don't know that anything happened. They are not aware of the fact that time has gone, has spent. Nothing. Absolutely nothing. I don't know that answers, but that's all I have.
The same as anesthesia then.
Yeah, anesthesia will certainly takes away your consciousness.
I have two questions. The first one concerns the need for scale. I mean, somehow this model...
The need for?
Scale. Why do you need something really big? Why can't we just build a computer with your model, your architecture? You know, we don't need to make it massively huge, right? Like,
no.
What is the role of scale? We don't need it.
Right.
Right. Okay. Well, that sounds too easy.
Well, do you understand that I have not, first of all, I haven't figured out all the things that are needed. I'm starting to go through and find some things that are not needed, some things that I do think are needed.
We've got a blackboard architecture.
I think it's just a blackboard architecture,
right.
And you're absolutely right. You don't need a huge amount of brain.
Right. So we're not trying to build the brain, we're trying to understand it. Okay, so my next question concerns motivation. Because we can easily build a robot that can perceive pain. That's trivial.
Well, in the sense of simulating it, or in the sense of knowing about it, but not feeling the agony.
And being the only thing on the stage and satisfying your requirements, okay? I think the hard part is actually motivation. Like, what is motivation? It seems qualitatively very, very different to the other things you're putting on the stage.
I think that the motivation is in the processors themselves. There are processors in the brain for pain, and when they are aware of pain, they get up on the stage. It's built into these processors to get up on the stage.
Well then, that seems easy as well, because essentially we're running a competition, and we're allowing some processors...
Oh, I'm not saying it's hard. You're absolutely right.
So why can't we do this right now? Why don't
Well,
we just
okay.
computer science and build it straight away?
Well, I would like to first finish with my model, and then I will go to it. I was telling you that I have a short term and a longer term. Yeah, I don't think it's going to be hard. We already know that the cerebellum, which has 80% of the neurons in our brain, 80%. And you know, there we know of. I have pictures here to show you of people who are missing half a brain. They're still perfectly conscious. I don't think it's hard. I think it's actually probably easy. I think that consciousness does arise in very low-level animals. That there is a beginning, and that beginning has to do with this stage, with this model.
So we probably have already actually done it in various robot architectures and things like that.
Well, that's what I'm not sure of, because I don't know of any robot that's built with this architecture.
There are lots of them. I mean, there are cognitive architectures that basically use this kind of model.
Yes, so I'd like to know about them.
Okay.
Send me email, please.
Maybe one last question, and then I'll ask people to take questions offline.
Great talk. Thanks. So my question is, what is the motivation behind building a conscious robot besides possibly besides that you want to understand consciousness, is there any other reason to want to build such a robot? Also, my second question is that it seems like feeling pain is not part of the requirements for consciousness according to this slide.
Right.
So why do you want to build a robot that can feel pain? If you want to just build a robot to understand consciousness.
Okay, I think the point is that pain is something we all really understand. We have all experienced the agony of pain, and I have no idea before this how the brain might conceivably cause that to happen. Now, maybe I don't have the full answer. That's possible. You may be able to come up with something even more better. But right now, I'm saying if all the processors know about it, you will feel the agony. Is that true or not? I would like to know. I personally want to know. It's also the case that DARPA will pay money for that answer. It wants to know how to cause its robots to feel pain. And you can understand why. A person who doesn't feel pain will damage themselves. Kids that are born with asymbolia, they don't feel pain. Kids that are born without that pain, they rarely live past the age of 3. There is one 5-year-old that actually, because of pain asymbolia, when she was 2 years old, they removed all her teeth because she was biting her lips and her tongue. She's actually been damaged quite a bit by what they had to do to keep her from damaging herself. She was running when she was 5, she's just 5 now, she was running not too long ago in the field, playing ball, and she broke a leg. And she knew that she should take care and stop. But she was having fun. She did a lot of damage because she kept on running. So the point is, there are reasons to want a robot to feel pain. Another really good reason is if I can make a robot feel pain when it hurts itself, I can make it feel even more pain when it hurts me. If I understand it, I can make that robot feel that pain that you know of when it hurts me. And I would like that. When it comes to, I've been asked a lot of questions about ethics. My answer about ethics is that no matter what you come up with there, you can be used for good, it can be used for bad, and I'm sure that will be true of this also.
Even though pain is not part of consciousness.
Well, I view it as part of consciousness. I view it, the whole thing as the same question.
That's thanks, Manuel.
Okay.
We have some refreshments on the side.